We're all dreaming of a future packed with self-driving cars, right? But that whole dream, it really hinges on one giant question. How do we actually prove they're safe? And I'm not just talking about keeping parts from breaking down. I mean, how do we make them safe from the built-in limits of their own design? Well, today we're going to pull back the curtain on the official engineering blueprint that finally gives us an answer to that question. Just how good is good enough?
Here's how we're going to break it down. First, we'll get into the weird paradox of how a perfectly working car can still be unsafe. Then, we're decoding the master equation engineers use to actually define safe. After that, we'll see how they simulate dangers that don't even exist yet, use data from us, human drivers, to set the bar, and finally, we'll reveal the absolutely staggering number of miles a car has to drive to pass its final exam. Okay, let's dive right into the heart of the problem. This is something traditional safety rules just were not designed to handle. It's a concept called SOTF, which is short for safety of the intended functionality. And, it creates a fascinating paradox.
Just think about that for a second. Imagine a car where everything is working exactly as it was designed. The sensors, they're sensing. The computer, it's computing. The brakes, they're braking perfectly. And yet, that car could still cause a crash. So how on earth is that even possible?
Well, the answer lies in looking at safety in two totally different ways. Traditional safety, the stuff we've had for decades, is all about preventing failures. What happens if your brakes just stop working? But SOTIF, this is a whole new way of thinking. It deals with the limitations of a system that's working perfectly. A great example is a camera. It's not broken, but one of its limitations is that it might mistake a dark shadow on the road for a real obstacle, causing the car to slam on the brakes for absolutely no reason. See? Nothing's broken, but that's a seriously dangerous situation. So, to get a handle on these new kinds of risks, engineers basically needed a new kind of math. Let's take a look at the formula that sits at the very heart of this entire safety blueprint. All right, there it is. Now, I know it looks a little intimidating, but trust me, it's way simpler than it looks. The best way to think about it is like a recipe. It's a recipe that connects how often a car might do something potentially hazardous to the actual real-world probability of that action causing a crash. We're going to break down all four of these ingredients one by one. So the first ingredient, that's the big one. It's the final goal. You can think of it as the rate of harm. This is the number that society and regulators and the car companies all agree on as the maximum acceptable accident rate. And the target here is almost always to be way, way safer than a human driver, sometimes even 10 times safer. Next up, we've got RRHB, the rate of hazardous behavior. This is the number that the engineers actually designed to. It's the concrete target. It tells them how often the system is allowed to do something a little bit risky, like braking for that ghost shadow we were talking about. Now, this is where it gets really clever. PEHB is the probability of exposure. Basically, it's the wrong place, wrong time factor. I mean, if the car brakes for a ghost shadow, but there's nobody behind you for miles, was it really dangerous? Of course not. This part of the recipe calculates the odds that one of those hazardous behaviors happens when it actually matters, like when you're in bumper-to-bumper traffic. And finally, we have the outcome. This last chunk of the recipe asks two really simple questions. First, if something dangerous happens in a risky situation, what's the chance that anyone, you or the other driver, can react in time to stop a crash? And second, if a crash is going to happen no matter what, how bad will it be? This is where real-world physics and human reaction times get baked into the equation. So, that's the recipe. But to see how this all works in the real world, let's put it to the test with a feature you might actually have in your car right now, automatic emergency braking, or AEB. Okay, so to test an AEB system for these SOTIF risks, engineers run literally thousands of virtual simulations. They plug in super specific numbers, like the car's maximum braking force and how fast those brakes can ramp up. And then they set a very clear threshold. If the car brakes for no reason for more than about a third of a second, boom, that gets logged as an official hazardous event. Now, when the engineers ran all these simulations, something totally unexpected and kind of backwards popped out of the data. It turns out that unnecessary braking at lower speeds actually caused more simulated rear-end collisions than it did at higher speeds. So why would that happen? Well, it comes down to pure human psychology, really. Think about how you drive. At 25 miles an hour, we tend to follow the car ahead of us way more closely than we do at 65 on the highway. That tiny little gap gives the driver behind you almost zero time or space to react if your car just suddenly decides to slam on the brakes. And this is a perfect example of why these simulations are so important.
This all brings up a really important question. We keep saying the car should be safer than a human, but how safe are humans, really? To set that target, engineers have to turn the microscope around and study us. And they have a really systematic 4-step process for this. They start by figuring out what could go wrong, they model it with math, just like we saw. But step 3 is the crucial one. They dive deep into mountains of real-world accident data to see how we humans actually perform out there on the road. That data is what tells them exactly what they need to be testing for.
So have a look at this. This table is built from real crash data from NHTSA, the National Highway Traffic Safety Administration. The key insight is hiding right here in this middle row. The speed range between 50 and 80 kilometers per hour, that's roughly 30 to 50 miles per hour, accounts for jaw-dropping 70% of all rear-end collisions.
Let's just visualize that for a second. This chart makes it crystal clear. Nearly 7 out of every 10 rear-end crashes happen in this middle speed danger zone. Now, this isn't just some random fact. This is a bright, flashing arrow telling engineers exactly where they need to focus their most intense, most rigorous testing. It's all about working smarter, not just harder. And that brings us to the final piece of this whole puzzle. We've got the benchmark from human drivers, we've identified the danger zones. So how does a car actually pass the final exam? Well, it comes down to one last bit of math. This formula here is what calculates the total test mileage a car has to drive. And it's not just about driving a ton of miles. It's about driving enough miles to prove, with a very specific level of statistical confidence, that the system is truly safer than the human benchmark we just established. So, what does the math say? When you run all the numbers to prove with 95% confidence that a car is safer than a human, you get this, a single powerful number, 3x. And this, right here, is the ultimate takeaway. To be statistically certain, we're talking 95% confidence, that a robot car is safer than us, it's not enough to just match our accident rate. It has to drive nearly 3 times that distance without a single one of these SOTIF-related failures. So if the human benchmark is, say, 1 accident every million miles, the car has to drive almost 3 million miles perfectly to pass the test. Which brings us to our final thought. For the first time, we have a rigorous, data-driven, mathematical blueprint to actually measure and validate the safety of robot cars. So the question really isn't, how can we know if they're safe anymore? The real question is, with all this, are we ready to trust the math?